This video is the first video covering Module 6, which is all about rational expressions and functions. So in the first video, we're going to talk about what a rational expression is and what a rational function is and how to perform operations on those rational functions by multiplying and dividing. So please make sure you're completing the guided notes as we go along. So a rational function is indeed a function, right? It passes the vertical line test. It's a function defined by a quotient of polynomials. So f of x is p of x over q of x, where q of x doesn't equal 0, right? Because we can never divide by 0. So it could be something that looks like f of x is x plus 3 over x minus 2. The numerator and the denominator are both functions, right? And the domain of the rational functions, so all possible x values it can take on, is every real number except those that make our denominator equal to 0. So for this made-up example, my domain would be every single number as long as it isn't equal to 2. Because if I substituted in 2 to this function, 2 minus 2 would give me 0. I divide by 0. So for this function, our domain is every real number except 2. And we're going to talk about how to find domains a little bit further on in the video. So the first rational function I'd like you to see is this reciprocal function. It's defined as y equals 1 over x. This is what its graph looks like. And you'll notice this looks so much different than graphs we've seen previously in this class, which have all been linear equations with positive, negative, 0, or undefined slope. So in this case, our domain is all real numbers except when x equals 0, because we can't have our denominator being 0. And I can write this in set notation or interval notation. You get to pick your favorite. And our range is y such that y doesn't equal 0, because since my numerator is 1, I can never have my function equal 0 because it's never going to be 0 on top. So we've got a vertical asymptote at x equals 0 because we can never divide by 0. An asymptote is a line that you cannot cross. And then we've got a horizontal asymptote at y equals 0, this line, right? Because my function's outcome will never be 0. Another function would be the graph of y equals 1 over x squared. Notice how our pattern, like our shape, changes in this case because x is squared. It means every time I square a positive, I get a positive, so it's never going to be negative. Again, I've got a vertical asymptote at x equals 0 because I can never set my denominator equal to 0. And since my numerator is a constant, it can never be 0 as well. That's why I've got a horizontal asymptote here too. My domain is the same as our reciprocal function, as long as my x doesn't equal 0. And my range in this case is when y is greater than 0, because it can never be negative. It can never be less than 0 or equal to 0. So to find the domain of rational functions, what we're going to do is we're going to factor our denominator if we need. Then we're going to set it equal to 0 and solve for the points not included in our domain. So for this first example, I have 7x minus 14. So I set this equal to 0. I can factor it by pulling out a 7 if I wish. And I set each of its parts equal to 0. 7 equal to 0 doesn't make sense, so we ignore that. I have x minus 2 equals 0. We add 2 to both sides. That means that x equals 2. 2 is not in my domain. This is a number I'm skipping over in my domain. So I could write this in interval set notation as x as long as x doesn't equal 2. Or I could go in interval notation, negative infinity to 2, union with 2 to positive infinity. For my second function, I have f of x equals 3 plus x over x squared minus 4 plus 3. And I need to set that denominator equal to 0. and then I factor it. Okay, what are the factors of AC that add up to B? So what are the factors of positive 3 that add up to negative 4? How about negative 1 and negative 3? I set each of my factors equal to 0 using the zero factor property. This is the last thing we learned in Module 5. I get x is 1 and x is 3. So now I have two values excluded from my domain. So my domain is all values of x as long as x doesn't equal 1 or 3. And I would have from negative infinity to 1, together with 1 to 3, together with 3 to infinity. I feel like set notation is the easier way to write these, but you do get to pick your favorite. So a couple special cases are here. My domain is a constant. So if I set that constant equal to 0, nothing's excluded. We could also think of this as 8x over 3 plus 1. Well, this is just a linear function. Its domain is going to be all real numbers because nothing is excluded. And I could write that as an interval as negative infinity to positive infinity. Here I've got x squared plus 4. Well, I can't factor that because it's a sum of perfect squares. So I'd get x squared as negative 4. And if I try and take the square root, we can't take a square root of negatives. Another thing you might notice is that my denominator would never be equal to 0, and my denominator would never be like negative because it's always an x squared. So this also has a domain of all real numbers, which we can also write as negative infinity to positive infinity. So next, let's practice graphing a few of these functions. And what we're going to want to do in order to graph these functions, we're going to want to pick 3 points on each side of our domain, and we're going to want to label our asymptotes where they appear. So here I have 5 over x. So I'd let x equal 0. This is not in my domain. So my domain would be all values of x as long as x doesn't equal 0. So now I need to pick out some x values to fill out this table. And I like to pick 3 on either side of the excluded value of my domain. So I'm going to pick negative 3, negative 2, and negative 1. And I'm going to pick 1, 2, 3. So starting with the positive numbers, if I have 5 over 1, that's 5. If I have 5 over 2, that's 2.5. If I have 5 over 3, that's about 1.6, repeating. And I can graph those points. When x is 1, y is 5. When x is 2, y is 2.5. When x is 3, y is 1.6. My function's going to look kind of like this, right? And because my pop is positive, it can never be equal to 0. So I'd have an asymptote at y equals 0. And you'll see a lot more of these in college algebra. I just wanted to make sure everyone had seen them once before you get there. Next, on the other side, I've got 5 over negative 3. That's negative 1.6. 5 over negative 2, that's negative 2.5. Notice the symmetry here. 5 over 1, that's negative 5. So I can label these points again, negative 5, negative 2.5, and it's going to look like this. It's changing directions. So this would be a graph of this function, right? We're plugging in x values to get out y values and plotting those points. Next, I got 10 over x minus 1. So I'm going to have x minus 1 equals 0. So that means x equals 1. This is not in my domain. It's going to be an asymptote. My domain is all values of x as long as x doesn't equal 1. So I put a little dashed line here because that tells me how my graph's going to be divided in 2. And then I pick some values on either side of it. So I'm going to pick 0, -1 and -2. And I'm going to pick 2, 3, and 4. So 10 over 0 minus 1 becomes 10 over -1, which is -10. 10 over -1 minus 1 becomes 10 over -2, which is -5. And 10 over -2 minus 1 becomes 10 over -3. That becomes -3.3 repeating. And I'm converting these to a decimal so they're easier for us to graph. So I have when x is 0, y is -10. When x is -1, it's -5. When x is -2, it's 3 1/3. So my graph is going to look like this. Again, my outcome can never be 0, so I'll have an asymptote y equals 0. If I have 10 over 2 minus 1, that becomes 10 over 1, which is 10. If I have 10 over 3 minus 1, that becomes 10 over 2, which is 5. If I have 10 over 4 minus 1, that becomes 10 over 3, which becomes a positive 3.3. Again, notice this kind of symmetry. So when x is 2, y is 10. When x is 3, y is 5. When x is 4, y is 3 1/3. My graph is going to look like this. So let's practice working with rational expressions. By working, I mean multiplying and dividing rational expressions. And we can't forget that we're going to need to remember all of our factoring skills, every single one. So let's go ahead and take a look at our first examples. So rational expressions, much like fractions, must be simplified. If I was told the answer was 2/4, no, I want that simplified into 1/4, right? So in order to simplify rational expressions, we need to factor both the numerator and the denominator, find their greatest common factor, and divide out those common factors. So for example 1, I have x squared minus 3x minus 18 over x squared plus 7x plus 12. And I told you factoring trinomials was going to be really important, and we need to be able to do it quickly. So I'm thinking, okay, what are some factors of -18 that add up to -3? How about -6 and 3? So that's going to be x minus 6 over x plus 3. That's how that's going to factor. And if you need to pause this video at any time so you can take your time factoring and work through these things, I suggest you do so. Next, I have x squared plus 7x plus 12. What are the factors of 12 that add up to 7? How about 3 and 4? So I have x plus 4 over x plus 3. We can see the greatest common factor is x plus 3. We cancel those out, and we're left with x minus 6 over x minus 4. That's our final answer when we're simplifying these rational expressions. So let's simplify the following. So I have y squared minus 4. That's a difference of squares. That's going to factor to y minus 2 times y plus 2. In my denominator, I have 2 times y minus 4. 2 is my greatest common factor. So I have 2 times y minus 2. Y minus 2 is the greatest common factor. Those are going to cancel. And I'm left with y plus 2 over 2. For problem 3, I have x cubed minus 27 over x minus 3. Luckily for us, that denominator is already fully factored. This trinomial is going to factor, I know, because it's a difference of cubes. So my a is x and my b is 3. Remember, this is the formula you have to memorize. So I have x minus 3 times x squared plus a times b, so that's 3x, plus b squared, which is 9. My x minus 3 terms cancel, and I'm left with x squared plus 3x plus 9, which cannot be factored any further. Okay, so let's go ahead and factor this numerator first. I'm going to have to factor by grouping. The greatest common factor of PR and QR is R. The greatest common factor of PS and QS is S. So I'm going to have R times P plus Q plus S times P plus Q all over the greatest common factor of my denominator, which is R, times p plus q. But I'm not done factoring by grouping. Remember, I have to collect my greatest common factors and what they left behind. And we see that our greatest common factor is p plus q. Those are going to cancel. I'm left with r plus s over r. And I can't just cancel out those r's because r and s aren't being multiplied together, right? If I had rs over r, then this would totally simplify to just be s. Because they're being added, we can't do that. An easier way to see it might be with numbers. So if I had 2 plus 3 over 2, that's really 5 over 2. I can't simplify that any further. But if I had 2 times 3 over 2, then I could cancel out those 2's because that'd be 6 over 2, which would give us 3. So when in doubt, feel free to break it up into some more real-world examples that aren't just using variables. So in general, if the numerator and the denominator are opposites, then the expression equals -1. So for example, I have q minus 7 over 7 minus q. First off, this should already make us feel a little iffy. We always want that variable term first. So I could rewrite this as q minus 7 over negative q plus 7. And then you think to yourself, what does Dr. Miller say about negative leading coefficients? And she probably says ew or gross or nope. So we want to pull out that greatest common factor in my denominator. So I have q minus 7 over negative q minus 7. These two terms are the same. They're going to cancel out, and I'm left with -1. Friendly note that r plus 2 over r minus 2 can't be simplified any further because there's no negative leading coefficient to remove. And here's that example all worked out. So you can check it for yourself. This is exactly what I did. I've got m minus 3 over negative m plus 3. We pull out that negative leading coefficient in my denominator. We see that these cancel, and I'm left with -1. If I have r squared minus 16, that factors into r minus 4 over r plus 4, because it's a difference of squares. I'm going to write this over negative r plus 4. We pull out that negative leading coefficient. I'm left with negative r minus 4. R minus 4, r plus 4. We can see in our numerators this is going to cancel. I'm left with r plus 4 over -1, and I can rewrite this as negative r minus 4 because I would just divide both terms by -1. Or I could leave it as negative r plus 4. When we're multiplying rational expressions, we multiply them the same way we're going to multiply fractions. But the first thing I want us to do always is to factor. First factor, then simplify your fractions. After that, we're going to multiply, but we're going to leave them in factored form so it's easier for us to see which of the common factors are going to cancel out. So for example, I have 5 times x minus 5 over x times 3x squared over 10x minus 10. So I have 5 times x minus 1. All that is times 3x squared over x times 10 x minus 1. We can see what's going to cancel here, but if we didn't, it's okay. So let's pretend that we only see that this x minus 1 is going to cancel out. That leaves me with 15x squared over 10x squared. And not x squared, sorry, just over 10x. And then I think, okay, x squared divided by x, that's just going to leave me with x. 15 and 10 have a greatest common factor of 5. So I'm going to have 3x over 2 as my final answer. Let's do some more examples. I have 5x squared plus 9x minus 2 times 3x squared over x squared minus x minus 6. So in my denominator, I'm going to have 6x times this trinomial right here, x squared minus x minus 6. What are the factors of negative 6 that add up to negative 1? That's going to be negative 3 and 2. And that's our shortcut rule that we can use because our leading coefficient here, our a, was 1. I can't do that for this. So I'm going to have to write it out, and I'm going to have to factor by grouping. Here my AC is negative 10. What are some factors of negative 10 that add up to 9? How about 10 times negative 1? 5x squared minus x plus 10x minus 2. And now I can factor by grouping. X times 5x minus 1 plus 2 times 5x minus 1 factors to x plus 2 times 5x minus 1. That's my greatest common factor. So I write this all out, and we can see that our x plus 2 terms are going to cancel. I also see that I have an x that's going to cancel and a factor of 3. So this would be 1 over 2. So my final answer would be a single x times 5x minus 1 over 2 times x minus 3. And you can leave this in factored form. I recommend leaving it in factored form. Let's try that again. For this next example, I'll just need to use my exponent simplifying rules. So I've got 20 x to the 4th, y to the 5th, over 8 times 25x. So that's 200. 8 times 25 is 200. X squared times x is x cubed, y to the 4th. That's going to leave me with 20 divided by 200. That's 1/10. So I'll have a 10 in the denominator. X to the 4th divided by x cubed leaves me an x. Y to the 5th divided by y to the 4th leaves me a y. So I'm left with xy over 10. When we're dividing rational expressions, we divide them like we divide fractions, and the fact that we keep, change, flip, right? So we're going to factor all numerators and denominators, divide out the common factors, keep the first function the same, change from division multiplication, and flip the second fraction. That's also called the reciprocal. So then we're going to multiply those numerators and denominators and leave it in factored form and keep simplifying if we need to. So here I have 8k minus 16 over 3k divided by 3k minus 6 over 4k squared. So let's factor everything. I've got 8k minus 2 over 3k times, we're going to go ahead and flip this and factor out a 3. So I'd have 3k minus 2 in my denominator and 4k squared in my numerator. When I multiply across, we can see these k minus 2's are going to cancel. That leaves me with 8 times 4, which is, it's been a long day, 32 k squared over 3k times 3, that's 9k. The only thing that's going to simplify out is that k, so I have 32k over 9. Let's try some more examples. Last examples of the video. So I have 1 over t squared minus 4 divided by t squared plus 6t plus 9 over t squared plus t minus 6. So let's factor everything first. My first denominator factors into t plus 2, t minus 2. And this is all divided by this, which is going to factor into t plus 3 squared, right? We could go ahead and write it out as t plus 3 times t plus 3. I think that might be easier for us in the long term because the factors of 9 that add to 6 are 3 and 3. Next, what are the factors of negative 6 that add up to positive 1? How about positive 3 and negative 2? We can already see that this t plus 3 is going to cancel. So I have 1 over t plus 2 times t minus 2 times, now we flip everything. T plus 3 is in my denominator, and t minus 2 is in my numerator. Those t minus 2's are going to cancel, So I'm left with 1 over t plus 2 times t plus 3, and we want to leave that in factored form. And that was the last example. So I hope you've seen in this video how crucial it is to have your factoring skills be very, very solid. So if you need more practice factoring, please go back and watch the Module 5 Part 1 and 2 videos so we can get our factoring skills up to par, because we're going to be factoring in the rest of Module 6, all of Module 7, and Module 8 as well.